Close your eyes, lie down, and take a slow breath. Let your body sink into the surface beneath you. Imagine your mind floating freely as we begin a journey to a world far from home. This is a world that has captivated human curiosity for centuries, a planet of red dust, vast plains, and distant horizons. Don't miss a night of fresh documentaries. Hit subscribe and share your location in the comments. What's the time in your corner of the world? All right, one more quick question before we begin. What would it mean to leave Earth and live on another planet? To feel the soil of a foreign world under your hands? To watch skies without clouds you recognize? The question itself invites wonder, but it is one built entirely on science, observation, and careful understanding. Mars has been called the red planet for the color of its soil, a hue caused by iron oxide that stretches across deserts and valleys, giving the surface a rusty orange-brown tint that glows under the weak sunlight that reaches it. But Mars is more than its color. It is a complex world with a story written in rocks, ice, and the patterns of ancient flows. To imagine living there, one must first know the place intimately, not as a backdrop for stories, but as a world governed by physical laws and conditions unlike our own. Mars is the fourth planet from the Sun, orbiting at an average distance of roughly 228 million kilometers, nearly 1.5 times farther from the Sun than Earth. Its day, called a sol, is slightly longer than Earth's, lasting about 24 hours and 39 minutes. The tilt of its axis is about 25 degrees, similar to Earth's, giving Mars seasons that mirror those on Earth, though they are roughly twice as long because the planet takes nearly 687 Earth days to complete an orbit. Mars is smaller than Earth, with a diameter of approximately 6,779 kilometers, just over half of Earth's, and a mass about 10% of Earth's. Gravity is weaker, only about 38% of Earth's, which would make a person feel far lighter on the surface. These fundamental characteristics set the stage for all other aspects of life and exploration on Mars. Even the thinness of its atmosphere, composed mostly of carbon dioxide, plays a role in shaping every aspect of daily life, from temperature regulation to the behavior of dust storms that sweep across vast regions. The surface of Mars is a mosaic of ancient landscapes. Vast plains stretch across much of the northern hemisphere, interrupted by ridges and cratered plateaus. The southern hemisphere is more rugged, pocked with deep impact craters that mark billions of years of collisions with asteroids and comets. Olympus Mons rises as the tallest volcano in the solar system, reaching nearly 22 kilometers above the surrounding plains, dwarfing any mountain on Earth. The Valles Marineris Canyon system stretches over 4,000 kilometers, a scar many times longer than the Grand Canyon, with depths reaching 7 kilometers. The scale of these features reminds us that Mars is a planet of extremes, shaped over eons by processes that continue in subtle ways even today. Its landscapes are a record of both violent events and gradual change, from lava flows to the slow erosion caused by wind and frost. Early observations of Mars reveal a history of human fascination. Ancient civilizations noted its reddish color and movement among the stars, sometimes associating it with gods of war or fire. Telescopic studies in the 17th century allowed scientists to see surface details, and early astronomers debated the nature of features that resembled canals. Today, spacecraft have replaced telescopes, sending detailed images and data that show a world far more complex and less hospitable than the dreams of earlier generations. The thin atmosphere, Cold temperatures and radiation exposure make Mars a challenging place for life as we know it. Yet these same conditions offer clues about the planet's history and the potential for future human presence. The Martian atmosphere is a faint veil, only about 0.6% as dense as Earth's at the surface. It is composed of approximately 95% carbon dioxide, with trace amounts of nitrogen, argon, and oxygen. Atmospheric pressure averages around 600 pascals, less than 1% of Earth's sea level pressure, which makes the air effectively unbreathable for humans. Temperatures vary widely, from highs near 0 degrees Celsius at the equator in summer to lows of minus 125 degrees Celsius at the poles during winter. Winds can whip across the surface at hundreds of kilometers per hour during dust storms that obscure visibility for weeks, moving fine dust particles that slowly reshape dunes and settle in regions far from their origin. These winds, though thin and low in force compared to Earth's, can carry abrasive dust that wears down equipment and challenges any long-term human presence. Mars experiences seasonal changes due to its axial tilt. The polar ice caps grow and shrink as carbon dioxide freezes and sublimates with the seasons, creating a dynamic landscape of frost, ice, and occasional water vapor clouds. Water ice is present beneath the surface in many regions and in the form of frost or snow near the poles. Evidence of ancient riverbeds and dried lake beds shows that liquid water once flowed more freely, carving channels and depositing minerals that now serve as records of the planet's wetter past. These features are not only scientifically intriguing, but also practically important. Water is a critical resource for future explorers, whether for drinking, growing food, or generating oxygen and fuel. Gravity, distance from Earth and sunlight all play a role in defining the living conditions. Mars's weaker gravity affects how materials settle and how a human body adapts over time. The lower sunlight intensity, roughly 43% of what reaches Earth, limits natural heating and energy production from solar panels. Dust in the atmosphere can further reduce sunlight reaching the surface, affecting power systems and climate control. These factors must be accounted for in any plan to live on Mars, from habitat design to clothing, food supply, and energy storage. Understanding these baseline conditions is the first step toward imagining life there, because every human need, oxygen, warmth, water, nutrition, is filtered through the lens of this planet's environment. Over decades, robotic missions have gradually unveiled the nature of Mars. Orbiters map the surface with high-resolution cameras, detect minerals with spectrometers, and measure atmospheric conditions with precision instruments. Landers and rovers touch the soil, analyze rocks, and even drill beneath the surface. Each mission adds a piece to the puzzle. Layered rocks reveal ancient lakes, small gullies hint at seasonal flows, and the presence of perchlorates indicates chemical complexity. Through this slow accumulation of knowledge, we begin to understand the constraints and possibilities of living on Mars. We see not a story of fantasy, but a framework built entirely on observation, measurement, and analysis. Mars remains a world of both challenge and fascination. Its red deserts, towering mountains, and frozen poles stand as monuments to natural processes far older than human life. Gravity, sunlight, atmospheric composition, and temperature extremes form a set of conditions unlike any on Earth, yet one that is now being studied with the possibility of human adaptation in mind. To live on Mars would require careful consideration of these realities. Each fact about the planet contributes to a larger understanding, a world of fragile balance where every habitability question is answered through physics, chemistry, and biology. As we begin to consider the ways humans might inhabit Mars, we start not with dreams, but with facts, letting the data guide the imagination toward what is scientifically plausible. Mars is a world where the air is thin, almost a whisper compared to Earth. Its atmosphere is made mostly of carbon dioxide, with tiny amounts of nitrogen, argon, and other gases. The pressure at the surface is very low, less than 1% of what humans feel at sea level on Earth. That means the air is too weak to breathe, and it cannot hold heat in the same way our atmosphere does. Temperature swings are extreme. During the day, the equatorial regions may reach near 0 degrees Celsius in summer, but nights plunge into deep cold, often below -70 degrees. At the poles in winter, temperatures can drop even further, reaching lows of -125 degrees. The thin air allows heat to escape quickly, and without clouds or water vapor to trap warmth, the surface cools rapidly when the sun sets. Seasons change slowly, lasting almost twice as long as Earth's due to the planet's longer orbit. Carbon dioxide freezes at the poles during winter, creating frost and thick ice layers that shrink again as spring returns. Dust is everywhere on Mars, lifted by wind that moves across plains and valleys. The atmosphere is light, so even gentle breezes can carry fine particles across long distances. Dust storms can grow enormous, sometimes covering the entire planet for weeks. The storms darken the skies, reduce sunlight, and coat surfaces in a fine red powder. These storms change the appearance of dunes and shift soil layers, slowly shaping the landscape over years. Dust can block solar panels, making energy collection difficult for machines or future human habitats. The thin air allows the wind to move at high speeds, though it pushes with less force than winds on Earth. Despite the light touch, the persistent movement reshapes the surface over time, scratching rocks and piling fine sand in new formations. The surface of Mars is varied and dramatic. There are high mountains, like Olympus Mons, a volcano that rises nearly 22 kilometers above the surrounding plains, towering higher than any peak on Earth. Valleys and canyons stretch for thousands of kilometers, with Valles Marineris reaching depths of 7 kilometers. These long chasms reveal layers of rock, telling a story of repeated geological activity and erosion. Plains dominate large regions, flat areas where dust and sand accumulate over time. Craters of all sizes are scattered across the surface, each a reminder of collisions with asteroids over billions of years. The southern hemisphere is especially rugged, full of impact scars, while the northern hemisphere has smoother plains and lowlands. Ice exists at the poles, primarily frozen carbon dioxide with water ice beneath. Seasonal growth and shrinkage of these ice caps reshape the poles with each orbit, creating a changing landscape of frost and ice. Radiation is another feature of the Martian environment. Without a thick atmosphere or a strong magnetic field like Earth's, the surface is exposed to cosmic rays and solar radiation. Levels of radiation are high enough to be dangerous for humans over long periods. Unprotected exposure could damage cells, increase the risk of cancer, and harm internal organs. Shielding becomes essential for anyone living on the planet. Ice, rock, or soil can block some radiation, so habitats will need to be built with protection in mind. The effect of radiation is constant, even when storms darken the sky. Unlike Earth, Mars offers little natural defense, so every human activity on the surface requires consideration of this invisible, persistent hazard. The weather is simple yet harsh. There are no oceans to drive storms, and rain does not fall. Clouds form occasionally from water vapor or carbon dioxide, and frost settles at night. Winds pick up and move fine sand across surfaces. During certain seasons, the temperature changes trigger pressure differences, pushing air from high to low regions and creating persistent breezes. Mars does not have storms like hurricanes, but the long dust storms can reduce visibility to nearly zero and block sunlight for days. Daily temperature cycles are sharp, with warmth during the sun's presence and swift cooling after it sets. Seasonal cycles change the amount of frost at the poles, the intensity of winds, and the likelihood of dust storms across regions. These factors combine to form a world that is cold, dry, and dynamic in its own slow rhythm. Every ridge, dune, and canyon on Mars carries evidence of the planet's past. Valleys suggest ancient flows of liquid, now long frozen or evaporated. Craters show the history of collisions and the age of the surface in different areas. Ice caps grow and shrink, shaping nearby terrain. Dust moves slowly across plains, leaving faint patterns that only careful observation can reveal. Small frost patches appear in morning shadows, disappearing as the day warms. Rocks show signs of erosion by wind, small scratches and grooves that map the passage of time. Even the light that falls on Mars is different, pale and filtered by the thin atmosphere, casting a reddish hue across the terrain. It is a quiet world, yet one full of activity on scales both large and small. Understanding the Martian environment is critical for imagining life there. Air is thin, cold, and unbreathable. Sunlight is weaker, dust can block energy, and radiation is a constant concern. Storms sweep the surface, temperatures swing wildly, and water exists mostly as ice. The geography is vast and varied, from enormous volcanoes to deep canyons, from smooth plains to rugged southern highlands. Ice caps move with the seasons, and wind sculpts the sand. All these features form a reality that must be accepted and understood before any human presence can be possible. Habitats must protect against cold and radiation. Energy systems must account for dust and weaker sunlight. Life support must ensure oxygen and warmth in a world that offers neither naturally. Mars is not hostile by choice, but by physics and chemistry, and humans must respond with careful planning and adaptation. The thin atmosphere, low temperatures, and high radiation together form an environment that is both mesmerizing and unforgiving. Observations from orbiters and rovers provide detailed data on wind speeds, temperature changes, and surface composition. Sensors detect dust, particle size, and movement, map polar ice extent, and track seasonal shifts. Thermal imaging shows how surface and subsurface layers heat and cool, revealing differences that affect potential habitat placement. Radiation monitors record cosmic ray penetration and highlight the need for shielding. This constant measurement builds a complete picture of the environment, offering guidance for future human activity and ensuring that every step taken on Mars is informed by observation rather than assumption. Life on Mars would require careful alignment with these natural rhythms. The changing seasons dictate energy availability, surface conditions, and the potential for water extraction from ice. Daily temperature swings influence habitat insulation and power requirements. Dust storms dictate operational schedules, solar energy, collection and exposure limits for both humans and machines. Understanding geography guides site selection, ensuring access to flat areas for landing and construction, nearby ice for water, and protection from radiation wherever possible. These factors intertwine, creating a picture of the planet as a living system, governed by predictable but challenging rules. Success on Mars depends on working with these rules, not against them, and respecting the slow, quiet rhythms of a world that has evolved independently for billions of years. Even small details matter. Frost forming overnight on rocks and soil indicates local temperature patterns. Shifts in dust dunes show prevailing wind directions and speeds. Seasonal shrinking of polar ice reveals where water might be accessible. Variations in radiation levels between valleys and plains influence safe travel routes. Understanding these elements allows humans to plan with care, adapt to local conditions, and make the most of the resources Mars offers. Each measurement and observation forms a layer of knowledge, building toward the practical reality of living on a planet so different from the one humans have always known. The environment is not only a challenge, but also a guide, showing where life is possible, what precautions are needed, and how to respect the forces of a planet that moves at its own pace and scale. Water is one of the most important elements for life, and Mars has a history with water that stretches back billions of years. Observations from orbiting spacecraft and rovers have revealed traces of water ice hidden beneath the surface and near the poles. In many regions, the ground contains frozen layers, sometimes just centimeters below the soil, sometimes deeper, forming a reserve that could be tapped for human use. Water on Mars today is mostly frozen or locked in minerals, but the presence of these reserves shows that the planet has not always been as dry as it is now. Scientists detect hydrated minerals in rocks, meaning water once reacted chemically with the surface, altering its composition. These minerals provide clues about the climate and environmental conditions long ago, painting a picture of a world where liquid water once shaped valleys, carved channels, and supported chemical reactions that may have been favorable to life. Some valleys on Mars are enormous, stretching for hundreds of kilometers, with branching patterns that strongly resemble river networks on Earth. These ancient riverbeds show clear evidence that liquid water once flowed across the surface, eroding rocks and transporting sediment. In places like the Valles Marineris system, layered sediments suggest repeated flows of water over long periods. Cratered basins often hold signs of dried lakebeds, indicating that pools of standing water existed, possibly for thousands or millions of years. Seasonal changes today reveal small, dark streaks on slopes, which may result from briny water flowing briefly during warmer months. These seasonal flows are not large rivers, but indicate that water is still present in some form and interacts with the surface, shifting soil, dissolving salts, and leaving chemical traces. The presence of water, both past and present, has profound implications for the possibility of life. Life as we know it requires water to sustain biological processes, transport nutrients, and support cellular activity. Ancient flows and lake beds suggest that microbial life could have existed in the distant past, when water was more abundant and temperatures were milder. Scientists search for chemical signs in rocks that may point to past life, looking for patterns of minerals formed in water or structures that resemble microbial mats. While no direct evidence of life has yet been found, the chemical and geological signatures indicate that conditions were once favorable. Mars preserves these signs well because its environment is dry and cold, which slows the processes that would otherwise destroy delicate traces of biology over time. Water is also critical for human survival. Any long-term presence on Mars would depend on reliable access to water for drinking, food production, and oxygen generation. Water can be melted from ice reserves or extracted from hydrated minerals. This water could be purified for consumption, split into hydrogen and oxygen for fuel or breathing, and used in hydroponic systems to grow plants. The availability of local water would reduce the need to transport massive quantities from Earth, which is costly and difficult. Understanding where water exists, how it behaves under local conditions, and the best methods for extraction are central to planning a sustainable human presence. Even small amounts of water can support life if managed carefully, and scientists continue to map and quantify these resources to guide future missions. Seasonal ice and frost cycles at the poles demonstrate the dynamic presence of water. During winter, carbon dioxide freezes out of the atmosphere, covering the polar regions with a layer of dry ice, while water ice remains as a stable layer beneath. In summer, the carbon dioxide sublimates, revealing the underlying ice and sometimes producing thin films of liquid brine under certain conditions. This seasonal cycle affects local temperature and soil chemistry, creating temporary changes in the availability of water. Understanding these cycles is important for designing systems that collect and store water. Any human settlement would need to anticipate periods when ice is accessible, when extraction is easiest, and when the risk of losing water due to evaporation or sublimation is higher. Rovers such as Curiosity and Perseverance have explored sedimentary rocks in regions like Gale Crater and Jezero Crater, revealing minerals that formed in water. Clay minerals, sulfates, and other hydrated compounds indicate that water once persisted long enough to alter the rocks chemically. Layers within craters show repeated wet and dry periods, suggesting that the climate shifted over time, sometimes wetter, sometimes drier. These findings help scientists understand how long conditions suitable for life may have existed, and where the best places to search for past life might be. The study of these rocks also informs where humans might find usable water or soil suitable for agriculture, guiding choices for future bases. The distribution of water across Mars is uneven. The poles hold the largest ice reserves, but permafrost exists at lower latitudes as well, often mixed with soil and dust. Some mid-latitude regions have patches of ice accessible near the surface, while deeper layers may store water kilometers below. These underground reservoirs could be tapped with drilling equipment, but doing so requires careful planning, energy, and infrastructure. The variety of water sources, from polar caps to subsurface ice, provides options for human use, but also emphasizes the need to study each location carefully. Understanding where water is most concentrated, how easily it can be accessed, and its chemical purity is essential for any long-term mission. Water also interacts with the planet's chemistry, producing salts and minerals that influence soil composition. Perchlorates, for example, are chemical compounds found in Martian soil that can absorb water from the atmosphere and create briny solutions. These chemicals pose challenges for agriculture and human health, but they also provide a mechanism by which water can exist in liquid form under the right conditions, even at low temperatures. Learning how to manage these chemicals, remove harmful substances, and take advantage of natural brines is part of planning for human survival. Soil and water are not separate resources. They interact, and understanding that interaction is key to building a safe and functional habitat. Water is essential not only for drinking and farming, but also for producing oxygen. Electrolysis can split water into hydrogen and oxygen, providing breathable air and rocket fuel. By locating ice deposits, melting or chemically processing them, and storing water efficiently, humans can generate a supply of oxygen independent of Earth. This reduces the need to transport large amounts of air or water from Earth, making self-sufficiency more realistic. Future settlements would combine water extraction, recycling, and oxygen generation to maintain life support systems in the harsh Martian environment. Water is the thread that connects survival, energy, and habitat sustainability. Understanding water on Mars extends beyond immediate human needs. It also informs our knowledge of planetary evolution and the potential for life elsewhere. By studying ancient lake beds, river channels, and hydrated minerals, scientists can reconstruct the planet's climate history and assess whether life could have emerged. These studies guide exploration strategies and provide insight into where humans might safely live and work. Water is a connector between past and future, a bridge linking ancient environments to the potential of human settlement. It remains central to every consideration of living on Mars, from daily survival to long-term planning, showing that a single element, present in small quantities, shapes the entire question of human habitation. Humans are shaped by the gravity of Earth. Our bones, muscles, and organs have adapted over millions of years to a world where every step presses us down. On Mars, gravity is only about 38% of what it is on Earth. This change is noticeable from the moment someone moves across the surface. Muscles that once supported walking and lifting experience less resistance, and over time they weaken if not exercised carefully. Bones, which maintain strength by constantly rebuilding themselves in response to stress, begin to lose density in low gravity. Joints may experience changes in pressure, and circulation adapts to a weaker pull toward the ground. The heart, accustomed to pumping blood against Earth's gravity, works differently. Blood pools less in the legs, but may rise more easily toward the head, affecting vision and balance. These effects, observed in astronauts on the International Space Station, illustrate the challenges of living in a reduced gravity environment for long periods. Radiation is another major concern for humans in space and on Mars. Outside Earth's protective magnetic field and thick atmosphere, cosmic rays and solar radiation strike constantly. In low Earth orbit, spacecraft provide some shielding, but radiation levels are higher than on the surface. On a journey to Mars and on the planet itself, exposure is significantly greater. Long-term radiation can damage DNA, increasing the risk of cancer and affect tissues and organs throughout the body. Shielding habitats with rock, ice, or specially designed materials helps reduce exposure, but no protection is perfect. Every step outside a habitat, every moment unshielded, carries risk. The intensity and persistence of radiation on Mars shape both daily activities and long-term health planning for potential settlers, influencing how missions are designed and how time is spent on the surface. Living on Mars involves not only physical stress, but also mental and emotional challenges. Isolation from Earth, confinement in small habitats, and limited social interaction can affect the human mind. On the International Space Station, crews experience weeks or months of separation from family and friends, controlled routines, and a lack of privacy. On Mars, communication delays of up to 20 minutes one way make instant contact impossible. Decisions may need to be made independently, and minor problems cannot be solved immediately by support teams on Earth. Over time, this isolation can lead to feelings of loneliness, stress, and anxiety. Structured routines, recreational activities, and careful planning of social interaction become essential to maintain psychological health. The mind, like the body, must adapt to a new environment. Sleep patterns on Mars are affected by slightly longer days and the absence of natural cues familiar from Earth. The daily rhythm, or circadian cycle, may shift, making it harder to maintain regular sleep schedules. Lighting inside habitats must simulate Earth conditions to help regulate rest, and careful attention to exercise and diet supports mental and physical well-being. Astronauts on long missions use controlled schedules, artificial lighting, and communication systems to reduce the effects of isolation. On Mars, these systems would be even more critical, as the extended journey, reduced gravity, and environmental stress combine to challenge human endurance. Exercise is one of the most important adaptations for the body. In low gravity, muscles used for walking, standing, and lifting weaken quickly. Bones lose minerals, leading to reduced density and higher risk of fractures. Cardiovascular fitness diminishes because the heart works less to pump blood. On the International Space Station, astronauts use resistance machines, treadmills, and cycles to counteract these effects. On Mars, exercise will remain essential, but gravity is higher than in orbit, meaning some natural loading occurs while walking or moving. Still, structured exercise is necessary to maintain strength, coordination, and health. The design of habitats, equipment, and daily routines must accommodate physical activity to prevent long-term degeneration. Nutrition also affects human adaptation. Calories must match energy needs in low-activity periods and when performing tasks under Mars conditions. Proteins, vitamins, and minerals are necessary to support bone density and muscle mass. Adequate hydration is critical in a dry, low-pressure environment where fluid balance can shift. Maintaining proper nutrition supports the immune system, mood, and overall performance. On long-term missions, food may come from stored supplies, hydroponic growth, or partially processed local resources, and all must be planned carefully to maintain health under unique environmental stresses. Mental health remains intertwined with the physical. Confinement and isolation magnify minor irritations and interpersonal tensions. On Earth, minor frustrations are resolved by space, movement, and social contact. On Mars, space is limited and social circles are small. Teams must develop communication skills, conflict resolution strategies, and routines that prevent fatigue or emotional strain. Psychological support can come from Earth via delayed communication, pre-recorded counseling, or peer support within the crew. Awareness of the mental impact of long missions is as important as understanding physical effects, because cognitive performance, decision-making, and morale influence survival and mission success. Radiation, isolation, and low gravity combine to create a complex picture for human adaptation. Bones lose density, muscles weaken, hearts adjust to new blood flow, and radiation damages DNA. Sleep and circadian rhythms shift, and psychological stress grows. Every system, from physical to mental, must be supported by careful planning, habit, and technology. Life support, exercise equipment, habitat design, nutrition, and social interaction all become part of a carefully calibrated approach to keep humans alive and healthy. Even small miscalculations can have large consequences over months or years on Mars. Long-term missions on Mars differ from experience on the International Space Station in scale and duration. The ISS provides a close approximation of microgravity for months at a time, but Mars introduces partial gravity, different day lengths, and greater isolation. Supplies cannot be delivered quickly. Repairs and medical emergencies must be addressed independently. Communication delays prevent real-time guidance, requiring crew autonomy. The environment is harsher, colder, drier, and more radiated than low Earth orbit. These differences make preparation, training, and system redundancy critical. Astronauts must be ready to handle medical situations, technical failures, and psychological challenges without immediate intervention from Earth. Living on Mars is a continuous balancing act, blending physical adaptation with careful planning and mental resilience. Even simple activities require adjustments. Walking across uneven terrain in lower gravity changes posture and balance. Lifting objects feels easier but affects muscle development differently. Daily hygiene, food preparation, and habitat maintenance must account for limited water, lower air pressure, and dust. The human body reacts to these stresses slowly, making it necessary to monitor health continuously. Medical equipment, exercise protocols, and monitoring systems help detect problems early. The goal is to maintain function, strength, and mental focus over months and years, ensuring that humans remain capable of performing essential tasks in an environment designed by physics, not imagination. Every factor of human physiology intersects with the environment. Gravity, radiation, isolation, nutrition, and exercise interact to shape health and performance. Changes are gradual but cumulative, requiring constant adaptation and planning. Understanding these interactions comes from decades of study on Earth, in orbit, and in simulated habitats. Data from long-duration spaceflight, medical studies, and analog missions inform the design of Mars missions. Predicting how humans will fare over multiple years on a foreign planet is challenging, but careful study and preparation provide a foundation for safety and survival. In the end, the human body is resilient, but requires support. Muscles, bones, and circulation adjust to gravity. Radiation must be shielded against. Minds must cope with isolation, and sleep, nutrition, and social interaction must be managed. Partial gravity and environmental stress create a new baseline for health and performance. Missions to Mars will rely on this knowledge, combining biology, medicine, and engineering to create conditions where humans can survive, work, and even thrive. Each piece of information, from bone density loss to psychological response, shapes the way settlements are designed, the way activities are planned, and the way humans interact with a planet that challenges every assumption about life. Traveling to Mars begins long before a rocket leaves Earth. The timing of the launch is crucial, determined by the positions of Earth and Mars in their orbits around the Sun. The most efficient path uses a Hohmann transfer orbit, an elliptical route that allows a spacecraft to move from Earth's orbit to Mars with minimal fuel. This path relies on precise calculations, taking into account the relative speed and position of the planets. Launch windows occur approximately every 26 months, when Mars is near its closest approach to Earth, called opposition. Missing this window can add months or years to a journey, making careful planning essential for both cost and crew safety. Scientists and engineers monitor planetary positions, trajectory calculations, and fuel requirements to determine the optimal time for departure. Even when the timing is perfect, the journey to Mars is long. Depending on the speed of the spacecraft and the exact trajectory, travel times range from 6 to 9 months. During this period, astronauts remain in confined habitats with limited space, moving along a curved path through the emptiness of the solar system. Life aboard the spacecraft is regulated by strict schedules to maintain health, exercise, and mental well-being. Supplies must be carefully rationed, and the habitat must provide air, water, food, and waste management. The long journey emphasizes the need for reliable systems, redundancy, and planning, because help from Earth will be delayed, and minor failures can escalate into serious risks over time. Rocket propulsion technology defines how humans reach Mars. Traditional chemical rockets use stored fuel and oxidizer to produce thrust, pushing the spacecraft off Earth and into orbit. These rockets are well understood and reliable, but require large amounts of fuel for long-distance travel. Nuclear thermal propulsion offers higher efficiency, using nuclear reactions to heat propellant and generate thrust. This method could shorten travel time, reduce fuel mass, and provide a steadier acceleration. Ion propulsion uses electric fields to accelerate ions, creating a continuous but gentle thrust. Though slower to start, ion engines can operate for months, gradually increasing speed with much less fuel than chemical rockets. Each propulsion type has advantages and limitations, and future missions may combine methods to optimize travel time, safety, and cost. Life support systems are critical for in-transit habitats. These systems provide breathable air, clean water, food storage, and waste management. Oxygen is generated, carbon dioxide removed, and air circulated to prevent buildup of harmful gases. Water is recycled from humidity, urine, and other sources, reducing the need to carry massive quantities. Temperature and pressure are carefully controlled, keeping the habitat comfortable and safe despite the cold vacuum of space. Radiation shielding protects astronauts from cosmic rays and solar events, using materials like polyethylene, water, or specialized alloys to reduce exposure. Sensors continuously monitor environmental conditions, alerting the crew to any deviations that may affect health or mission success. Habitat design must accommodate both functionality and human psychology. Space is limited, so living quarters are compact with modular designs that allow movement, storage, and work in confined areas. Sleeping areas are often individual compartments, allowing privacy in a shared environment. Workstations are arranged to optimize efficiency for scientific experiments, navigation, and communications. Recreational areas provide limited space for exercise, relaxation, and social interaction, all essential for maintaining mental health during the months-long journey. Every surface, every storage container, and every piece of equipment is arranged for safety and practicality in microgravity conditions. Exercise aboard the spacecraft is essential to counteract the effects of low gravity. Muscles weaken, bones lose density, and circulation changes in the absence of normal gravitational forces. Treadmills, resistance devices, and cycles provide controlled stress on the body to maintain strength and endurance. Exercise also supports mental well-being, offering structure and a sense of routine during the long trip. Habitats include specialized equipment to allow astronauts to exercise effectively within limited space, balancing physical needs with the constraints of mass, energy, and design. Maintaining consistent physical activity is a key factor in preparing the body for Mars gravity upon arrival. Food must be carefully planned for both nutrition and storage. Meals are designed for long shelf life, often dehydrated or packaged to preserve vitamins and prevent spoilage. Water content is limited to reduce mass, and food is sometimes rehydrated before consumption. Growing fresh food during the journey is a possibility for future missions, using small hydroponic or aeroponic systems that recycle water and nutrients. These systems provide psychological benefits as well, offering a connection to living plants and a sense of routine. Every calorie, every nutrient, and every portion is calculated to support health, performance, and the ability to withstand the physical and mental stress of space travel. Waste management is another essential function. Solid waste is collected, stored, or recycled depending on mission design. Urine and wastewater are filtered and reused to recover water. Carbon dioxide exhaled by astronauts is removed from the air using scrubbers, and oxygen is replenished through chemical or mechanical means. Managing waste efficiently reduces risk of contamination, prevents buildup of harmful substances, and ensures that resources like water and air remain available throughout the journey. Effective waste systems are vital for both short-term comfort and long-term survival. Radiation exposure during the trip remains a persistent concern. Spacecraft design incorporates shielding to protect against galactic cosmic rays and solar particle events. Storage areas, fuel tanks, and water containers can provide additional barriers, and crew members are trained to move to safer areas during solar events. Monitoring instruments detect changes in radiation levels, allowing adjustments to schedules and activities. The long duration of travel means that even low-level exposure accumulates, making shielding, monitoring, and planning critical to prevent harmful health effects during and after the journey. Every detail of transportation to Mars is interrelated. Propulsion determines speed and trajectory, which influences travel time and exposure. Life support systems ensure survival, nutrition, and hygiene, which affect physical health and psychological resilience. Habitat design shapes movement, rest, and work, all while balancing mass and energy limitations. Exercise, radiation protection, and waste management interact with each other, forming a complex system that must operate reliably for months without resupply. Planning, testing, and redundancy are essential to ensure that humans arrive safely and in sufficient condition to begin life on Mars. Even small deviations in trajectory can affect arrival conditions. The spacecraft must be guided precisely to enter orbit around Mars or land on the surface at a safe location. Navigation relies on a combination of sensors, ground-based communication, and onboard calculations. Adjustments are possible through controlled burns or course corrections, but each maneuver consumes fuel and requires careful calculation. Failure to account for small errors can lead to missed landing zones or unsafe velocities, emphasizing the importance of precision and planning. Transportation to Mars is not merely about speed, but about control, safety, and coordination between human, mechanical, and environmental factors. Psychological preparation is as important as physical preparation. The crew must be ready for months of limited contact with Earth, confined spaces, and repetitive routines. Exercises in simulated environments, team-building activities, and mental health strategies are part of pre-flight training. During the journey, communication with Earth is delayed, requiring patience and independence. Maintaining morale, focus, and cooperation is critical to prevent errors, maintain health, and ensure mission success. Transportation to Mars is a test not only of engineering, but also of human endurance, requiring careful preparation, monitoring, and adaptation over a long period of time. Ultimately, the journey to Mars combines the challenges of physics, biology, and psychology. Launch windows and transfer orbits dictate timing. Propulsion systems determine speed, and habitats sustain life. Life support, exercise, nutrition, waste management, and radiation protection form an interconnected network of systems designed to support humans for months in space. Every calculation, every design choice, and every procedure aims to ensure that the crew arrives on Mars ready to begin the next phase of exploration. The voyage is long and difficult, demanding patience, planning, and careful execution. But it is the first step toward making the Red Planet a place where humans might one day live. Living on Mars for long periods will require a reliable supply of food. Carrying all the food from Earth for months or years is not practical, so growing food on the planet becomes essential. Scientists have explored two main options: growing plants in Martian soil or using hydroponic systems. Martian soil, called regolith, contains minerals and nutrients that plants need, but it also contains salts and chemicals that can be harmful. Before planting, the soil may need to be treated to remove toxins, supplemented with nutrients, and managed to hold water. Hydroponics, on the other hand, uses nutrient-rich water to feed plants without soil. This system allows precise control of water, nutrients, and root conditions. Both methods aim to provide fresh vegetables, fruits, and herbs to maintain a healthy diet, while also helping recycle carbon dioxide into oxygen within a habitat. Light is essential for plant growth, and Mars receives only about 43% of the sunlight that reaches Earth. Dust in the atmosphere and the planet's greater distance from the Sun further reduce the intensity of natural light. Greenhouses on Mars may use artificial lighting, such as LEDs, to supplement sunlight. These lights provide the specific wavelengths that plants need for photosynthesis. By controlling light cycles, intensity, and duration, crops can grow steadily despite seasonal changes or dust storms that block sunlight. Careful management ensures that plants remain healthy, productive, and nutritious, providing a consistent food supply even when natural conditions are limited. Gravity on Mars is weaker than on Earth, which affects how plants grow. Roots and stems respond to gravity as they develop, guiding orientation and strength. In lower gravity, roots may grow differently, water distribution in the soil changes, and the transport of nutrients within the plant can be slower. Scientists experiment with different planting techniques, containers, and support systems to ensure that plants develop normally. Hydroponic and aeroponic systems can help reduce gravity-related issues by controlling water and nutrient delivery, supporting steady growth despite the unusual conditions. Observing plant growth in these environments also provides insights into what adjustments may be necessary for humans working in reduced gravity on Mars. Nutrition is a critical concern. Astronauts require a balanced diet that includes carbohydrates, proteins, fats, vitamins, and minerals. Fresh crops can supply some of these needs, especially vitamins and antioxidants that are difficult to store for long periods. Preserved and stored foods supplement fresh produce, providing a consistent source of calories and nutrients. Careful planning ensures that the diet supports physical strength, bone density, and immune function, particularly in conditions of reduced gravity and increased radiation. Food systems on Mars must balance availability, variety, and quality, helping to sustain both physical and mental health over extended missions. Experiments on Earth have provided valuable insights into growing food in conditions similar to Mars. The Mars Desert Research Station in Utah, for example, simulates isolation, limited resources, and environmental constraints. Crew members grow small crops, manage water, and monitor plant health while living in confined habitats. These experiments help researchers understand practical challenges, including soil treatment, nutrient management, and the psychological benefits of tending plants. Hydroponic systems tested in these analog habitats show that controlled water and nutrient delivery can produce reliable yields, even when natural conditions are limited. Lessons learned in these environments guide the design of future Martian greenhouses and food systems. Water management is a central challenge. On Mars, water is scarce, so growing food requires careful recycling and efficiency. Hydroponic systems minimize water loss by circulating water through plant roots, collecting excess, and reusing it. Soil-based methods also require precise irrigation to prevent waste and ensure plants receive enough moisture without overwatering. Water quality, temperature, and delivery timing are all carefully monitored. Efficient water use not only sustains crops, but also supports the broader life support system by conserving this vital resource for drinking, hygiene, and oxygen production. Temperature control is equally important. Mars is cold, and habitats must maintain warmth for both humans and plants. Greenhouses may be insulated, heated, or partially buried to protect crops from extreme temperatures. Thermal management ensures that plants remain within optimal ranges for growth, avoiding stress from cold nights or fluctuating conditions. Monitoring systems track temperature and humidity, making adjustments as needed. Stability in these conditions helps plants develop consistently and reduces the risk of crop failure, which is critical for long-term survival. Pest and disease control is another consideration. Although Mars has no native pests, the closed environment of a habitat can allow mold, bacteria, or fungi to spread quickly. Careful sterilization, monitoring, and habitat design reduce the risk of contamination. Hydroponic systems can be easier to manage in this regard because they are enclosed and allow precise control over water and nutrients, limiting opportunities for pathogens. Clean and controlled environments protect both crops and humans, maintaining a safe and productive food system. The psychological benefits of gardening should not be underestimated. Caring for plants provides structure to the day, a connection to life outside of technology, and a sense of accomplishment. Tending crops, observing growth, and harvesting food contribute to well-being and morale, helping to offset the stress of isolation and confinement. These benefits have been observed in analog habitats on Earth and are likely to be important for Mars crews, giving humans a tangible connection to living processes in an otherwise mechanical and controlled environment. Energy use for food production is a practical concern. Lighting, heating, water pumps, and nutrient circulation require electricity. Solar panels, nuclear reactors, or other energy sources must be sufficient to support agriculture along with other life support functions. Careful energy planning ensures that crops can grow consistently without overtaxing the habitat's resources. Efficiency in these systems supports sustainability, making it possible for humans to maintain food production over long periods, even when sunlight is limited or environmental conditions change. Crop selection is guided by nutritional needs and environmental suitability. Fast-growing plants with high nutrient content, such as lettuce, spinach, and radishes, are preferred. Other crops, including tomatoes, peppers, and herbs, provide variety, flavor, and additional vitamins. Experimentation continues to determine the best mix of crops for both nutrition and psychological benefit. Trials on Earth help identify species that are resilient, efficient, and productive under controlled conditions, offering a roadmap for successful Martian agriculture. In summary, growing food on Mars requires careful attention to soil quality, water management, light, temperature, gravity, and nutrients. Hydroponic systems complement soil-based methods, ensuring reliable and productive crops. Experiments in analog habitats demonstrate that humans can grow food while living in isolation and under environmental constraints. The lessons learned inform the design of habitats, greenhouses, and life support systems, ensuring that crews have both sustenance and a connection to living processes. Food and agriculture are central to survival, health, and morale, providing a foundation for life on the red planet. Mars offers resources that can support human life if used carefully and efficiently. One of the most important strategies is in situ resource utilization, or ISRU. This approach means using materials found on Mars itself, rather than bringing everything from Earth. Water, oxygen, and fuel can all be produced from local sources. Water is found mostly as ice beneath the surface, or mixed with soil and minerals. By heating ice or extracting water from hydrated minerals, humans can obtain liquid water for drinking, agriculture, and life support. This water can also be split into hydrogen and oxygen through electrolysis. The oxygen provides breathable air, while the hydrogen and oxygen can be combined as rocket fuel for further travel or power generation. ISRU reduces dependence on Earth shipments and allows a settlement to become more self-sufficient over time. Regolith, the loose layer of soil and rock that covers Mars, contains minerals that can be useful for construction and industry. Metals such as iron, aluminum, and magnesium exist in Martian soil and can be extracted for use in building structures, machinery, or tools. Processing regolith requires careful handling because it is fine and abrasive, and some minerals may contain toxic compounds. Techniques like heating, chemical treatment, and magnetic separation can isolate useful materials. Over time, these methods allow settlers to create parts, repair equipment, and build infrastructure without constantly relying on Earth supplies. Mining regolith is both a practical necessity and a step toward sustainable living. Manufacturing on Mars involves turning local materials into usable products. 3D printing, sintering, and other additive manufacturing techniques can transform powdered regolith into bricks, tiles, or structural components. Metal extraction and alloy production allow the creation of tools, mechanical parts, and even habitat supports. By producing materials on site, humans can adapt to changing needs, replace worn equipment, and expand habitats without waiting for shipments from Earth. Each successful production cycle builds independence, making long-term habitation more feasible. Manufacturing also encourages innovation, as settlers develop new methods tailored to the unique properties of Martian resources. Energy is a cornerstone of all these processes. Solar panels capture sunlight to produce electricity, though dust storms and the planet's greater distance from the Sun reduce efficiency. Nuclear reactors offer a steady, reliable source of energy, capable of supporting life support systems, manufacturing and water extraction, even during extended periods without sunlight. Batteries and other energy storage systems help maintain a constant power supply, storing excess energy during periods of peak production. Energy planning is critical because every industrial process, from water extraction to 3D printing, relies on reliable electricity. Efficient use and storage ensure that essential operations continue without interruption, even in challenging environmental conditions. Water and oxygen production are continuous needs. ISRU systems can melt ice, extract water from minerals, and recycle wastewater within habitats. Oxygen is separated from water molecules to support breathing, and hydrogen can be combined with carbon dioxide from the atmosphere to produce methane fuel. This chemical reaction, called the Sabatier process, provides a renewable source of rocket fuel, allowing future missions to refuel without relying on Earth. Integrating these processes into a habitat system allows settlers to maintain life support, power and fuel generations simultaneously, reducing risk and increasing self-sufficiency. Temperature control affects resource processing as well. Many chemical reactions, water extraction methods, and manufacturing processes require specific temperatures to operate efficiently. Habitats and processing units are insulated, sometimes partially buried, to maintain stable conditions. Heating systems powered by electricity or nuclear energy ensure that processes continue even during extreme cold or long nights. Proper thermal management increases efficiency, reduces energy waste, and supports continuous operations, which are essential for survival in a harsh and unpredictable environment. Soil and mineral handling require careful techniques to prevent contamination and mechanical wear. Fine dust can infiltrate machinery, reducing efficiency or causing failures. Enclosed processing units, filters, and regular maintenance help manage these risks. Workers and robots must also operate safely in contact with regolith that contains abrasive or potentially toxic compounds. By developing systems and protocols for safe material handling, settlers can maintain productivity while minimizing health risks and equipment wear. Mars's resources are valuable, but require respect and careful management to be useful. Long-term industrial processes must balance energy, labor, and material availability. Extracting water, producing fuel, manufacturing parts, and generating power all compete for resources. Efficient scheduling, automation, and integration of systems ensure that each process complements others rather than overloading habitat capacity. Data monitoring, predictive maintenance, and resource tracking are essential tools. A failure in one system can cascade into others, so redundancy and adaptability are crucial. Sustainable settlement depends on coordinating energy, material, and human effort to create a functioning, resilient ecosystem. Using local resources also reduces transportation costs and risk. Each shipment from Earth is expensive, slow, and limited by launch windows. By producing water, oxygen, fuel, and construction materials on Mars, settlers reduce dependency on these resupply missions. This independence allows expansion of habitats, longer missions, and even preparation for travel to other locations in the solar system. Resource utilization transforms Mars from a place where survival is fragile to a planet where humans can begin to establish a foothold, adapting to the environment rather than constantly relying on Earth. Experiments on Earth and in orbit provide lessons for Mars. Simulated habitats and processing units test water extraction, oxygen production, and material manufacturing in controlled conditions. Lessons learned in these analog systems inform design, energy requirements, and safety protocols for Mars. Robots and automated systems demonstrate how machinery can operate in dusty, low-pressure environments. Combining human skill with automation ensures efficient and safe utilization of resources, preparing settlers for the challenges of long-term life on Mars. Even small efficiencies make a difference. Recovering water from air, reusing waste products, or recycling materials reduces the burden on energy systems. Careful measurement and monitoring prevent waste and maximize output. Over months and years, these efficiencies accumulate, supporting larger populations and more complex operations. Every improvement in process, every refinement in technology, and every adaptation to local conditions increases the sustainability of life on Mars. In conclusion, Mars resource utilization integrates multiple systems to support life. Water, oxygen, and fuel are produced locally. Regolith is mined for construction and manufacturing, and energy systems sustain these processes. Efficient planning, technology, and experimentation allows settlers to become less dependent on Earth, increasing safety and sustainability. By combining chemistry, engineering, and careful management, Mars can provide the resources necessary for human survival, supporting the long-term development of habitats, industry, and exploration beyond the initial missions. Resource utilization is the backbone of life on Mars, turning challenges into opportunities for growth and self-sufficiency. Living on Mars brings challenges that go beyond survival and basic needs. One of the first issues is communication with Earth. Signals travel at the speed of light, but the distance between the planets creates delays. At its closest approach, messages take about 4 minutes each way, and at the farthest distance, more than 20 minutes. This delay makes instant communication impossible. Settlers cannot rely on immediate instructions or guidance. They must make decisions independently, relying on their own judgment and training. Computers, artificial intelligence, and automated systems can assist with data analysis, navigation, and problem-solving. But the human crew must remain in control of critical decisions. Autonomy becomes not just practical, but essential for safety and efficiency. Robotics plays a central role in exploration and construction. Rovers have already shown how machines can navigate Martian terrain, analyze soil and rocks, and perform scientific experiments. On future settlements, robots will help build habitats, maintain equipment, transport cargo, and even support agriculture. Automated systems can work continuously without fatigue, reducing the physical burden on humans. Advanced robotics may include remote-controlled devices, autonomous construction machines, and drones that monitor conditions from above. By combining human oversight with robotic precision, settlements can grow faster, safer, and more efficiently than relying solely on human labor in a harsh and unpredictable environment. Governance on Mars will be different from governance on Earth. Small populations living in isolated habitats require rules, laws, and decision-making structures that ensure safety, fairness, and cooperation. Conflicts must be resolved quickly and effectively to prevent tension from escalating. Governance may rely on a combination of pre-established protocols, crew agreements, and adaptive leadership based on experience. Decisions about resource use, schedules, exploration priorities, and safety protocols need clarity and consensus. Social structures will evolve as populations increase, balancing authority, individual freedom, and shared responsibility. The small size of the population amplifies the impact of interpersonal relations, making communication, trust, and cooperation essential to daily life. Healthcare on Mars must be robust and self-sufficient. Medical emergencies cannot rely on immediate Earth-based support. Facilities will need equipment to handle injuries, illness, and psychological issues. Preventive care, regular checkups, and monitoring of physical conditions will be essential. Telemedicine can provide delayed consultation, but training for the crew in medical procedures is critical. Stocking medical supplies, maintaining diagnostic tools, and developing emergency protocols ensures that even severe cases can be managed effectively. Long-term missions may require planning for childbirth, vaccination, and routine care as populations expand and human presence becomes more permanent. Health systems must adapt to the unique environment of Mars, from reduced gravity to radiation exposure, and to the challenges of isolation and confined habitats. Population growth and planning are intertwined with resources, habitat design, and life support. Initially, only small crews will be sent, but future settlements may expand if infrastructure, food production, and energy are sufficient. Careful planning is necessary to ensure that resources match the number of inhabitants. Habitats must provide living space, privacy, work areas, and recreation. Social systems must evolve to maintain harmony, prevent conflict, and support mental health. Expansion requires foresight in construction, logistics, and governance, preparing for new arrivals while maintaining sustainability for those already on Mars. Safety planning extends to emergencies beyond healthcare. Dust storms, equipment failures, radiation events, and habitat breaches pose real threats. Contingency plans, emergency shelters, and redundancy in critical systems reduce risks. Regular drills and training keep crews prepared for unexpected events. Communication delays with Earth mean that Mars inhabitants must be able to respond quickly without waiting for instructions. Safety culture becomes a central aspect of daily life, informing procedures, design, and decision-making. Every activity, from driving a rover to conducting experiments, is planned with risk mitigation in mind. Psychological and social dynamics play a significant role in small, isolated populations. Habits, routines, recreation, and structured interactions support morale. Confined spaces and limited social circles increase the potential for stress, tension, and conflict. Planning social activities, rotation of duties, and spaces for privacy help maintain well-being. Understanding human behavior in small groups over long periods informs both governance and habitat design. Social challenges may evolve as settlements grow, requiring new rules, conflict resolution methods, and leadership structures. Technology, communication tools, and environmental design all contribute to a supportive social environment. Resource allocation affects social organization. Access to water, food, power, and space must be fair and efficient. Decisions about priorities, whether for scientific research, habitat expansion, or daily needs, impact the entire community. Transparency, shared responsibility, and agreed-upon rules help prevent disputes. Systems for monitoring, distribution, and usage provide structure, ensuring that essential resources are managed sustainably. Small populations amplify the effects of shortages or mismanagement, so careful planning is critical to long-term survival and social stability. Education and training become ongoing activities on Mars. Crew members must understand engineering, medicine, biology, and navigation, in addition to their specific mission roles. Cross-training ensures that skills are available when needed, even if specialists are absent or incapacitated. Knowledge sharing, documentation, and practice simulations maintain readiness for complex situations. Education also supports psychological well-being by providing purpose, routine, and intellectual engagement. Settlers develop resilience not only through physical preparedness, but through continuous learning and problem-solving. As the settlement grows, infrastructure must support both daily life and future expansion. Roads for rovers, landing pads for spacecraft, storage facilities, energy grids, and communication networks all require careful planning. Robotics, autonomous systems, and human labor must be coordinated to maintain, repair, and expand these systems. Infrastructure provides the framework for governance, social interaction, safety, and resource management. Without it, the settlement would remain fragile, vulnerable to both environmental hazards and human error. In summary, technological and social challenges on Mars are intertwined. Communication delays force autonomy. Robotics enables exploration, construction, and maintenance. Governance and social structures support cooperation, fairness, and stability. Healthcare, emergency planning, and population strategies ensure survival. Daily life, long-term planning, and expansion depend on integrating technology, social management, and human adaptability. Success on Mars will not rely solely on machines or habitat design. It will rely on humans working together, using knowledge, and adapting to an environment that is both beautiful and unforgiving. Each element of this system, communication, robotics, governance, health, and social structure, contributes to a settlement that is resilient, functional, and capable of supporting life in a place far from Earth. Communication between Mars and Earth is never instant. Even at the closest approach, signals take several minutes to travel from one planet to the other. When Mars is farther from Earth, the delay grows to more than 20 minutes. This delay makes direct, real-time control impossible. Instructions from Earth arrive too late for immediate action. Settlers must rely on their own judgment, training, and decision-making. They cannot wait for guidance for every task. Systems must be designed to operate with autonomy, allowing humans to respond quickly to emergencies, make adjustments, and solve problems without waiting for Earth's support. The distance between the planets defines how humans plan, act, and interact with technology, creating a constant awareness that life on Mars is independent from Earth. Autonomy affects many aspects of daily life. Automated systems monitor air, water, temperature, and power levels. Sensors detect changes in pressure, humidity, or chemical composition. Alerts notify the crew of deviations, allowing corrective action. Humans oversee these systems, but machines handle constant monitoring and adjustments. Autonomous life support reduces the need for constant attention and ensures safety even when the crew is busy, asleep, or working on other tasks. This balance between human oversight and automation is critical because Mars conditions can change unexpectedly, and the crew must be able to respond to both routine operations and emergencies. Remote operations are used when humans cannot directly perform tasks. Robots on Mars already explore terrain, study rocks, and gather data. In the future, more advanced robots will help build habitats, transport materials, and maintain infrastructure. Some robots can be controlled remotely from Earth for planned activities, but communication delays make this approach limited. More often, robots operate under human supervision from the Martian surface itself, allowing immediate adjustments to unexpected situations. Combining remote control with on-site oversight gives flexibility. Humans guide robots when needed, while machines handle repetitive or hazardous work independently. This partnership extends human capability, making exploration and construction safer and more efficient. Robotics for exploration is essential because Mars is vast and challenging. Surface rovers analyze soil, map terrain, and test equipment. Drones or aerial vehicles may survey areas unreachable by ground vehicles. These machines can carry sensors, cameras, and instruments, transmitting information back to humans for interpretation. By using robots for reconnaissance, humans can plan routes, identify safe landing zones, and monitor environmental conditions. Robots act as both eyes and hands, performing tasks that would be too risky, slow, or resource-intensive for humans alone. Their work enhances safety, increases efficiency, and supports scientific research, forming the backbone of initial exploration efforts. Construction on Mars also relies heavily on robotics. Habitats, storage units, landing pads, and protective barriers need to be built before and during human occupation. Automated machinery can prepare foundations, assemble structural components, and perform heavy lifting. Robotic arms, 3D printers, and modular construction systems allow parts made from Martian regolith to be shaped into usable structures. Humans supervise, adjust, and operate machinery when tasks require judgment. But robots do much of the repetitive and labor-intensive work. Using robots reduces risk to humans, speeds up construction, and allows habitats to expand safely, even before large crews arrive. Maintenance of life support and infrastructure requires continuous attention. Automated systems check oxygen levels, water supply, power distribution, and temperature regulation. Robots can repair broken pipes, replace filters, and transport tools or parts. Predictive maintenance is key. Sensors detect wear, corrosion, or mechanical stress before failure occurs. Alerts enable humans to act before conditions become dangerous. By combining robotic precision with human problem-solving, habitats remain safe and functional, minimizing risks that could threaten survival. Continuous upkeep ensures that the settlement can operate independently for months or years. Automation extends to energy and water management as well. Solar arrays, nuclear reactors, and energy storage systems can operate with minimal human input. Software controls battery charging, energy allocation, and prioritization for critical systems. Water extraction, recycling, and purification are also automated, using pumps, filters, and sensors to maintain constant supply. The crew monitors these systems, but the machinery ensures stability and reliability. Automation allows humans to focus on exploration, scientific work, and habitat management, reducing fatigue and error while increasing resilience in an unforgiving environment. Safety relies on coordination between humans and robots. Dust storms, temperature extremes, and mechanical failures pose threats. Robots can inspect structures, survey terrain, and perform high-risk tasks. They act as scouts and helpers, preventing humans from facing unnecessary danger. Human operators maintain oversight, make decisions, and intervene when systems encounter unexpected problems. This combination ensures that critical operations continue smoothly, reducing hazards while enabling expansion and adaptation. Safety is built into the interplay of technology and human judgment, creating a dependable system for life on Mars. Scientific research also benefits from robotics. Automated instruments measure radiation, soil composition, atmospheric conditions, and chemical properties. Robots can collect samples, prepare them for analysis, and store them for later study. Data gathered by machines allows humans to make informed decisions about agriculture, resource extraction, habitat expansion, and exploration routes. The continuous flow of information strengthens understanding of Mars's environment, helping settlers adapt effectively and plan future growth. Humans and robots work together to turn raw data into actionable knowledge, guiding the settlement towards self-sufficiency. Training for robotic operations is ongoing. Astronauts must understand software, mechanics, and control systems. Skills include operating remote devices, interpreting sensor data, troubleshooting, and programming simple routines. Cross-training ensures that multiple crew members can operate critical systems if one person is unavailable. Simulations on Earth, in orbital stations, and in analog habitats help prepare crews for the unique challenges of Mars. Familiarity with robots and autonomous systems becomes part of daily life, integrating machines into every aspect of living and working on the planet. This preparation ensures that humans can effectively manage and rely on robotic support. In summary, communication and robotics are central to life on Mars. Delays require autonomous systems and independent decision-making. Remote operations complement human oversight, extending reach and capability. Robots perform exploration, construction, and maintenance, while automation supports life support, energy, and water systems. Safety, efficiency, and research all rely on this interplay between human skill and mechanical precision. By combining technology with careful planning and training, settlers can navigate Mars's harsh environment, expand habitats, and build a functional, sustainable settlement, making humans less vulnerable to the challenges of living far from Earth. Life on Mars requires more than survival systems and technology. It requires order, rules, and social structures that allow people to live together safely and efficiently. Small populations confined to habitats cannot function well without clear governance. Even minor disagreements over resources, schedules, or responsibilities could escalate quickly. Leadership structures may begin with appointed or trained commanders who oversee daily operations and decision-making. Rules will cover resource allocation, work duties, safety procedures, and conflict resolution. Agreements on priorities, responsibilities, and conduct help ensure that the small community functions smoothly, even in extreme isolation. Governance on Mars must balance authority with cooperation, giving enough control to maintain safety while allowing personal autonomy to reduce stress and resentment. Laws and regulations will be adapted to the unique environment. Standard Earth laws may serve as a reference, but practical adjustments are necessary. For example, rules about energy use, water rationing, or habitat access may be critical to survival, while more typical social laws address fairness, dispute resolution, and communal decision-making. Agreements may also cover scientific experiments, exploration permissions, and communication protocols. Small populations require flexible governance that can evolve as the community grows and new challenges arise. Decision-making must be transparent and participatory, ensuring that all members understand the rationale behind rules and feel invested in the settlement's stability. Healthcare on Mars must be self-sufficient. The crew must be able to handle illnesses, injuries, and emergencies without immediate help from Earth. Habitats will be equipped with medical supplies, diagnostic tools, and equipment for emergency procedures. Crew members receive medical training before departure and maintain skills during the mission. Routine health monitoring detects problems early, preventing small issues from becoming critical. Telemedicine can provide delayed guidance from specialists on Earth, but delays mean the crew must act autonomously. Maintaining physical health is essential, particularly in low gravity, where bones weaken, muscles atrophy, and the immune system can behave differently. Continuous monitoring and proactive treatment protect the well-being of every individual. Emergency planning extends beyond routine medical care. Contingency protocols address habitat breaches, fires, toxic exposure, radiation events, or structural failures. Redundant systems, shelters, and drills prepare the crew for unexpected scenarios. Psychological emergencies also require attention. Isolation, confinement, and high stress can lead to mental health crises. Support systems, private spaces, and structured routines help maintain mental well-being. Crew members must be trained to recognize early warning signs, provide peer support, and administer interventions when necessary. Safety planning combines physical and psychological preparedness, ensuring that the community can respond effectively to any threat. Psychological support is an ongoing requirement. Daily life on Mars can be monotonous, stressful, and socially constrained. Structured routines, recreational activities, and opportunities for creative expression contribute to mental health. Interaction with plants, robotics, or small animals in controlled environments can provide emotional benefits. Group exercises, social events, and communication with Earth, even delayed, help maintain morale. Attention to mental health is as important as life support systems, because stress, anxiety, or interpersonal conflict can undermine the functionality of the habitat and the safety of the crew. Psychological well-being is carefully managed alongside physical survival. Population growth strategies require careful planning. Initial crews are small, but expansion will depend on resources, habitat capacity, and life support capabilities. Strategies may include rotational arrivals of new settlers, carefully monitored childbirth, and education about responsible population growth. Each new member affects resource availability, social dynamics, and operational workload. Planning ensures that growth does not exceed habitat capacity, which could threaten health, safety, or stability. Sustainable expansion relies on integrating resource management, infrastructure, and social systems to support a larger population over time. Social dynamics are shaped by confined spaces, shared responsibilities, and reliance on others for survival. Cooperation is essential, and roles may rotate to prevent fatigue or resentment. Privacy, recreation, and communication opportunities help maintain personal well-being. Leadership must manage conflict carefully, balancing authority with fairness. Trust is vital. Each crew member depends on others for safety, resource management, and operational success. Effective social structures prevent disputes, foster teamwork, and maintain morale. As populations increase, social systems must adapt, including new rules, leadership methods, and governance mechanisms to maintain harmony. Education and training are integrated into daily life. Crew members continuously learn skills necessary for habitat maintenance, scientific research, medical care, and emergency response. Cross-training ensures that knowledge is distributed and that critical functions can continue if a crew member is absent or incapacitated. Simulations, workshops, and ongoing learning provide structure and mental engagement. Education also contributes to long-term settlement planning, preparing new arrivals for life on Mars, and equipping everyone with the knowledge to manage habitats, resources, and social interactions effectively. Knowledge sharing supports resilience, efficiency, and safety. Infrastructure supports governance, health, and society. Living spaces, workstations, laboratories, and recreational areas are arranged to allow efficient movement, privacy, and collaboration. Redundancy in energy, water, and air systems ensures that failures do not compromise survival. Communication networks, both internal and external, allow coordination, monitoring, and delayed Earth communication. The layout of habitats, placement of life support, and access to essential resources all influence social interactions, safety, and daily operations. Properly designed infrastructure helps prevent conflicts, supports mental well-being, and enables smooth governance. Integration of governance, health, and social systems is essential for long-term sustainability. Decision-making, law enforcement, medical care, psychological support, and education are interconnected. Policies about resource use affect health and social harmony. Emergency protocols tie together life support, medical readiness, and leadership response. Education ensures that crew members understand both technical operations and social responsibilities. By maintaining this integration, settlements can function efficiently, respond to challenges, and expand over time. Life on Mars requires that all these systems work in concert, with each aspect reinforcing the others for safety, stability, and growth. Ultimately, governance, health, and social management are as vital as technology and resources. Laws, rules, and social structures provide order. Healthcare and emergency planning protect physical and mental well-being. Population strategies and social dynamics maintain stability, cooperation, and morale. Education and infrastructure support knowledge, transfer, readiness, and long-term expansion. Together, these elements create a resilient human presence on Mars, capable of functioning independently, adapting to challenges, and sustaining life far from Earth. The success of a Martian settlement depends not only on machines, habitats, and supplies, but on the ability of humans to govern, care for each other, and build a society that thrives in a new and demanding world. The vision of living on Mars combines both scientific planning and human imagination. Space agencies and private companies have outlined timelines that vary depending on technology, funding, and risk tolerance. NASA has long-term plans for robotic missions that continue to map the surface, study the atmosphere, and test resource extraction techniques. Crewed missions are tentatively scheduled for the 2030s, with small crews sent to test habitats, life support systems, and the practicalities of survival on the surface. ESA, the European Space Agency, collaborates with partners on exploratory missions, emphasizing robotics, research, and preparatory habitat technologies. SpaceX has proposed ambitious timelines with the goal of sending humans within a few years, aiming to develop reusable rockets and systems capable of transporting larger numbers of settlers. These plans are flexible, adjusted by discoveries, failures, and new innovations. Each timeline reflects a slow, deliberate progression, recognizing that safety, technology, and sustainability must guide every decision. There is no rush. The journey to Mars is a long, methodical process of testing, learning, and adapting. Understanding what it takes to live on Mars extends beyond technology and resources. Philosophically, human settlement on another planet represents a profound expansion of our species. It challenges the idea that humans are confined to Earth and prompts reflection on what it means to survive in an alien environment. Living on Mars would mean learning to coexist with a landscape that does not support life naturally. It would require careful management of every resource, from air and water to food and energy. Humans would be responsible for both themselves and the delicate balance of the systems that allow them to survive. Becoming a multi-planet species is not only a matter of technology, but also a shift in perspective, an acceptance of responsibility and interdependence with our surroundings. Environmental ethics also play a role in the vision of Mars colonization. Humans must consider the consequences of introducing habitats, machinery, and chemical processes into a pristine and largely untouched environment. Resource extraction, construction, and waste management have the potential to change the landscape and affect natural processes. Scientists and planners emphasize minimizing harm, carefully selecting sites for settlements, and avoiding contamination of areas that may harbor signs of past or present microbial life. Sustainability principles guide decision-making, ensuring that human activity on Mars does not irreversibly damage the planet, and that resources are used efficiently to support life without creating long-term hazards. The goal is to establish a balance where humans can live, explore, and grow while respecting the Martian environment. Practical considerations continue to define the vision. Every aspect of life, from habitat design and energy production to food systems and healthcare, must integrate with the environment and available resources. Habitats must provide protection from radiation, temperature extremes, and dust storms. Energy systems rely on solar or nuclear power, with storage to maintain operations during periods without sunlight. Water and oxygen are extracted and recycled continuously. Food production combines hydroponics, soil-based cultivation, and nutrient supplementation. Automation and robotics reduce human risk while supporting exploration and maintenance. Governance, social structures, and healthcare ensure cooperation, stability, and resilience. Each element depends on the others, forming an interwoven system capable of sustaining life over months, years, and potentially decades. The vision also involves the daily life of settlers. Humans living on Mars would follow structured routines that combine scientific work, habitat maintenance, education, and recreation. Mental health and social well-being are as important as physical survival. Structured schedules, private spaces, and communal activities help maintain morale. Exploration, research and creative work provide purpose and engagement. Settlers would gradually expand habitats, test new systems, and prepare for larger populations. Each day would involve observation, adjustment, and learning as humans adapt to the slower rhythms and unique challenges of Martian life. Life on Mars is not an adventure in the traditional sense, but a deliberate, measured process of survival and growth. Over time, the vision extends to permanent presence and expansion. Initial crews will test systems, gain experience, and refine procedures. New arrivals bring additional skills, labor, and diversity, gradually building a self-sustaining community. Resource utilization, habitat construction, energy production, and agricultural systems improve with experience. Automation, robotics, and human effort combine to expand living space, support larger populations, and enable more complex scientific and industrial operations. Expansion is guided by careful planning, environmental ethics, and sustainability, ensuring that growth does not outpace available resources or compromise safety. Human settlement on Mars raises questions about identity and purpose. Living on a planet that was never meant to host humans requires adaptation, cooperation, and respect for the environment. Ethical considerations include how to balance exploration with preservation, how to treat potential life, and how to make decisions that impact future generations. Humanity's presence on Mars would reflect both our curiosity and our responsibility. It is a challenge that tests ingenuity, patience, and the ability to live in a system where every decision has consequences for survival. Philosophically, it is a reminder that survival is not passive. It requires deliberate, informed, and conscientious action. Scientific understanding continues to guide the vision. Every mission, experiment, and observation informs decisions about habitat design, resource management, and human health. Radiation studies, soil analysis, water extraction tests, and energy simulations contribute to a growing knowledge base. Lessons from analog habitats on Earth, orbital research stations, and robotic missions provide practical insights. Each discovery leads to adjustments in plans, improved safety protocols, and refined technology. Science remains the backbone of the vision, ensuring that plans are realistic, evidence-based, and adaptive to new information. Even as technology progresses, living on Mars remains a slow, careful process. Every stage, from robotic exploration to small human crews to larger settlements, requires testing, adaptation, and validation. Risks are high, and failure can be costly. Timelines may shift, missions may be delayed, and unforeseen challenges will arise. The pace is dictated by the need for safety, reliability, and sustainability. This deliberate progression is not a drawback, but a measure of wisdom, ensuring that each step builds a foundation for the next, and that human life on Mars is supported by knowledge and preparation. Ultimately, the question of whether humans will live on Mars is not a matter of possibility alone, but of patient, methodical effort. The answer will unfold over decades as technology, science, and human resilience advance. Life on Mars is envisioned as a careful blend of preparation, adaptation, and ethical stewardship. It is a journey that combines curiosity with responsibility, risk with planning, and imagination with practical knowledge. Each experiment, mission, and decision contributes to the slow, steady process of establishing a human presence beyond Earth. In conclusion, the vision of living on Mars encompasses timelines from agencies like NASA, ESA, and SpaceX. The philosophical shift to multiplanetary existence and careful consideration of environmental ethics and sustainability. Settlers must adapt to extreme conditions, rely on science and technology, and build social systems that support long-term survival. The process is gradual, guided by evidence, observation, and careful planning. Living on Mars remains a scientific journey, measured and deliberate, reminding us that exploration is not only about reaching new places, but about understanding how to live there safely, sustainably, and responsibly.